Chapter 5 is Introduction to Chemical Bonding. One thing I want you to point out is that although we may be getting into some of the complexities of the topic, we have actually already covered some of these in previous discussions and previous chapters. So this won't be entirely new, which is excellent. So if we look at this, one of the things that we find right away is that a chemical reaction changes the chemical properties of the substances. So if we have two things that are actually extremely poisonous originally, elemental sodium with its chemical symbol of Na, and chlorine gas with exists as a diatomic molecule of Cl, chlorine atoms, tied together by a bond, these combine to form NaCl, which is sodium chloride, and sodium chloride is table salt. So we have an incredibly poisonous gas and an explosive on contact with water metal that obviously you can't eat, and then you put this together and you get table salt. And so how does this work? Well, this works because there's a chemical reaction that takes place. And there's a chemical reaction that takes place because it has to form a stable set of atoms. And one of the ways it does that, in fact the way it does that in this case, is by the exchange of electrons. So how this works was originally investigated by G.N. Lewis and formulated as Lewis bond theory. And what the main points of this are that it's the valence electrons, the ones on the outermost orbit, that are the most important. And you can visualize why this would be so, because these are the ones that are going to bump into other atoms, the ones on the outermost edge. Now these valence electrons can do two different things. We talked about naming these things earlier, but now we're going to talk about how they actually occur. They can form ionic bonds, where the electrons are actually transferred from one atom to another. And when they're transferred, that's going to leave the atom they left slightly more positive and the atom they go to slightly more negative. And that's going to make a positive and negative ion, and those ions will then be attracted to each other because positives and negatives have attraction. It's called electrostatic attraction. Now covalent is where they share electrons. So we have some electrons that are in a cloud around one nucleus. We have a second nucleus that comes in and overlaps its electrons. Its electron orbit space, that space where the electrons would be, it actually overlaps and sits between the two atoms. Well, we have the positive nucleus of one attracted to the electrons attracted to it. And then we have a second positive nucleus who also has an attraction to the electrons, who have an attraction to it. So those two sets of attractions effectively attract both nuclei to each other. So that keeps two different atoms attracted to each other. In either case, what we form is what we refer to as a chemical bond. And this chemical bond is going to either give us a full orbit because of exchange of electrons, or it's going to give us a full orbit because of sharing of electrons. And that full orbit is a stable configuration, meaning that it's not going to react any further at that point. And having a full outer orbital, because it most commonly occurs when there are 8 electrons in that outermost orbital. They call it the octet rule, oct meaning 8. So the way we draw this is we actually draw the elemental symbol in the center, and then we surround it by a number of dots. And those dots are going to be equal to the number of valence electrons. We're going to ignore all the ones in the middle. So for silicon, for instance, we have 14 protons in the center, which means we're going to have 14 electrons altogether, 2 in the first orbit, 8 in the second, 4 in the third. But we don't really care about anything other than those 4 outermost ones. So we're going to ignore those inner or core electrons. When we then draw this, in a way that we can use to make pictures of how different elements are connected together with their chemical bonds, we're going to draw dots around that particular atom. And we're going to draw them in 4 different spots: above, to the right, underneath, and to the left. Kind of like north, south, east, and west here. So we're going to draw first 1 electron in each spot. These electrons are negative. They're trying to stay away from each other. So we kind of visualize, not even a word, we envision that the electrons are staying away from each other. After they move to these 4 different locations, if we had more electrons than that, they would start pairing up. So, for instance, if we if we had neon, which has 10 electrons, so that means it has 2 electrons in the first shell and 8 electrons in that next shell. So we have basically these sets of orbitals and those electrons. We would have to draw 8 electrons. So we'd start drawing 1 dot in each of the 4 directions. And then we draw a second dot in each of the 4 directions for the second 4. Okay, so this represents the 8 electrons around a neon nucleus. And this is what it looks like if you have to start pairing them up, if you have more than 4. And if we have somewhere in between, then some of them will be paired up and some will not. Now these chemical bonds happen when you get together elements and you have them in the correct ratios so that everything can either have an octet because it's given up or taken in electrons, or everything has an octet because it's sharing electrons. Let's look at the Lewis model of ionic bonding first. Okay, so this is ionic bonding. Specifically, it's the transfer of electrons. So if we have a sodium atom with its 1 valence electron, and we have a chlorine atom with its 7 valence electrons, when these react, what's going to happen is the electron from sodium will go to chlorine. And when that happens, we're going to end up with a sodium atom, which has the next inner core of electrons. But we'll just show this as completely empty. Completely empty just means that whatever is further in is a full orbital, and we're all set in that regard. For the chlorine that's just picked up an electron, now it has 1 extra. So instead of 7, it has 8. And in both cases now we have a completely full or completely empty, meaning the inner core is full, set of electrons. To indicate that this is now an ion, we usually put brackets around it and the charge in the upper right hand corner of those brackets. So for each of these, we'll put brackets and the charge. Now because these are now positive and negative, they form an electrostatic attraction to each other, and we represent them as a bond, as a bonded set of atoms. Right, so that's why sodium and chlorine form sodium chloride, because when they transfer electrons to be like a noble gas and have an octet, meaning a full, complete outer shell, and remember the sodium is complete because the inner core, the one that remains after that 1 is gone, is now a full 8 electrons. We don't show that because we're just showing the outermost, and we showed that outermost one leaving. But each of these have a octet or full valence shell, outermost shell, and when they form that full shell, they form charges, and then the charges attract to each other. Okay, so steps. Let's write that out. I've said that 3 times now, but let's write it. So electrons transfer so that they get to the octet. Okay, so they want to end up with an octet. They transfer electrons for that to happen. Okay, once they have an octet, there are now positive and negative charged ions. And then the ratio that they combine in is whatever gives a zero charge, net charge. So if we look at magnesium, for instance, and magnesium initially starts with 2 dots. Fluorine starts with 7 because of where it is. Okay, so when it becomes the ion, it gets to have an octet, it's going to give up electrons. And when it gives up those electrons, those extra electrons are going to go to the fluorine. And when they're in the fluorine, now the fluorine has 8 total electrons, 1 more than it started with, meaning it's a -1 charge in each of these cases. The magnesium now has an inner core with a full octet, now that it got rid of the 2 on the outer edge. Its new outermost edge, that inner sphere, is going to have 8, but that's 2 less electrons than we started with. So that means that it's +2. So the compound that this forms, magnesium fluoride, is MgF2. 3 steps happened all over again. We had electrons transferred to get to an octet. We had charges form because of that transfer. We have a ratio of atoms due to the charges canceling out and becoming 0. +2 and -1 and -1 gives us 0. Okay, so we can do the same thing with calcium oxide. Calcium, 2 dots. Oxygen, 6 dots. Now remember, we know how many it has because we can look at the periodic table. And we have already determined in the previous chapters how to use the periodic table to determine the number of valence electrons present in that particular atom. Okay, so step 1, transfer. Okay. Step 2, that means that there are charges formed now that they have an octet, where calcium wants to get rid of 2, so it can be like its nearest noble gas. Oxygen wants to gain 2 electrons, so it can be like a noble gas. That's going to leave these with +2 and 2 more electrons than it started with for oxygen. So -2. So when they combine, calcium oxide is a 1-to-1 ratio. +2 and a -2 give us a net 0 charge. Right? And this little slide explains all of that. Okay, now covalent bonds are a little different. Covalent bonds have overlap. So the orbital space, place where the orbital electrons would fit on this chlorine atom, right? So here, 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 and here, is going to overlap here in the center with the orbitals that the left-hand chlorine has. So it has 4 spaces, 1, 2, 3, and then 4. So this center pair of electrons is shared between each of the chlorines, and that gives them overall an octet of electrons each. Okay, so we can picture how they start, each of them having 7 electrons. We can kind of picture them this way. And then we can kind of picture that these 2 electrons can share, so that now the left side has 2, 4, 6, 8 electrons, and the right side, chlorine, has 2, 4, 6, 8 electrons also. Okay, so they both have an octet, so therefore they both end up with 8 electrons and are stable. when they combine in a 1-to-1 ratio. Now this is not ionic. We have no -1 charge. We have no chlorine ions. Okay? So this is not what's going on. These are not losing an electron, gaining an electron situations here. They're sharing. They're not going to form ratios that correspond to the charges being neutralized. They're going to form whatever ratio allows them to share in a way that gets them all an octet of electrons. Okay? We refer to those electrons now that are in between the ones that are shared as bonding pair electrons. Okay, so now this gets more and more complicated as we go. And as we add additional molecules, we're going to have to come up with some sort of system to make this work out without having to figure out where those electrons have to be and how we have to situate them and all of that sort of thing. So if we develop this system, it's easier to do this as a, how do we refer to that? As an algorithmic approach. Okay? So let's do this in steps. Step 1, we're going to take the molecule and we're going to find the one that's farthest from fluorine. And now, the farthest, we're just talking about physical distance on the periodic table. So you put your pen tip on fluorine, you start drawing a line to whatever other elements are there in the molecule. Whatever one you have to go the farthest to get to, that one is going to be the one that's in the center. Okay? Now the exception to this is hydrogen. Now the reason that hydrogen is an exception is because hydrogen only needs 2 electrons in order to have a full noble gas type configuration, right? That first shell is only big enough to contain 2 electrons. So if it's like helium, it has 2 electrons. Because it only can have 2, I can't form bonds between this and more than one other object. So what that means is in chemistry and in nature, we only find hydrogen on the outside edges of molecules, never in the center. And so let's actually have a molecule here. Let's say carbon tetrachloride, okay, CCl4. And we'll start using this algorithm right here on the carbon tetrachloride. So carbon is farthest from fluorine, just physically distance-wise on the periodic table. So we draw carbon in the center. Not too bad. Okay, so just carbon in the center. That's all we have so far. Next, we're going to draw the other atoms in that same north, south, east, west configuration around the center. So chlorine, 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 chlorine. Excellent. Step 3, we're going to connect with one bond to the center. Okay, and we're going to draw this bond as a line. And that line means 2 shared electrons. Okay, so shared electrons as a covalent bond. But it's a little easier to envision the connection if we draw those two, kind of picture them in there in this single attaching bond. So let's draw that. Excellent. Alright, now now that we have everything connected, now we have to determine how many electrons we really have to add to this molecule that we're drawing the structure of and the connectivity of, and how many we have left after making those bonds. So we count available electrons. Okay, so carbon had 4 electrons. We have 4 chlorines with 7 each, 7 valence electrons each. So 7 times 4 is 28 electrons. So total here, we have 4, 28, 32. All right, not bad. So 32 electrons. How many did we use? Well, we used 2 for each of these bonds. So 2, 4, 6, 8 electrons have been used, leaving us with 24. All right. If we have electrons left over, step 5 is we're going to add those electrons in pairs to the outermost atoms first to make octets and then move on. Okay, so we have the carbon, chlorine, 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 chlorine. I have 24 electrons to do something with, so let's start adding them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Notice that once it has 8, I move on. 19, 20, 21, 22, 23, 24. When I run out, when I get to 24, we stop. Whether we've used enough or we haven't used enough, we stop once we get to the total amount of electrons I had left. I can't just add in electrons to make things work. If it doesn't work, I have to do something else. Okay, so at this point, we check. Okay. If we all have octets, octet, then we're done. That's the shape, that's the connectivity of that molecule. That's the case we have here, so we're all set. There we go. So let's look at another possibility. Okay. Let's look at the O2 molecule, for instance. Okay. So for the O2 molecule, we're going to do the same thing. Farthest from fluorine, it doesn't matter because they're both the same. So I draw that in the middle. I draw the other ones around it. The only other one we have is another oxygen. Step 3, connect them with a single bond. Set. Step 4, calculate out the number of electrons that I have. Okay, let's see. I have oxygen, which is 6 electrons, and there's 2 of them, so that's going to equal 12 electrons. I've used 2 in the bond, so minus 2, which are used, means I have 10 electrons left. Okay. Step 5, add them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Aha! Alright, so this one on the right has 1, 2 in the bond, 3, 4, 5, 6, 7, 8. It has an octet. It is happy. The one on the left, however, 1, 2, 3, 4, 5, 6, does not have an octet. So if you're short electrons, what you have to do is make multiple bonds. What that means is you're going to have to shift the electrons that are already on the one with an octet towards the other atom. So we'll take these two, for instance, and shift them in between to make another bond. And what we have left then, bond, bond, is 2, 4, 6, 8 for the one on the right, 2, 4, 6, 8 for the one on the left. We've formed what's referred to as a double bond. This is actually a stronger and shorter bond than a single bond that we had before. Stronger, shorter. Okay, so this stronger, shorter bond means several things chemically. It means it's harder to break up. It means there's more energy in it when it does break apart. It means all sorts of interesting things. Plus it means it's shorter, so structurally we have to deal with the length of that bond when it interacts with other molecules and other atoms. Right? But this is what happens. If we don't have an octet and everything, if we're short, then we make multiple bonds. Okay, let's look at another one that has multiple bonds so we can see what that looks like. Okay, let's look at CH2O. So step 1. Farthest from fluorine, with the exception of hydrogen, is carbon. So carbon in the center. Step 2. Put the rest around the outside. There we go. You don't have to make it look symmetric. It doesn't really matter for the Lewis structure, this Lewis dot structure, which that's what these are called. But symmetric looks nice, so I tend to make them symmetric. Connect them each with a line. Line, line, line. Okay, and then count up how many we have available to finish this off. Carbon is 4. Hydrogen gets me 1 times 2. 2 electrons. Oxygen gives me 6. So 6 electrons. Altogether, 12 electrons to play with. I've already used 2 for 6. So that means I only have 6 electrons left. Alright, so I start putting them in around the outside. Well, I can't put them on hydrogen. Hydrogen already has its octet with 2. I know octet means 8, but that's still what we refer to it as when it has a full outer shell. Oxygen and carbon don't have a full octet. So we have 6 left. We start adding them to the outside ones first. 1, 2, 3, 4, 5, 6. Alright, that is an octet, but we're out. It may look like we're done, but this is the same as the last case because carbon here only has 2 for 6 electrons. So what do we do next? Multiple bonds, right? So we're going to take from one that has enough, shift those in between, and then that gives us this is our final structure. And now hydrogen has 2 and 2. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. That structure is right. Huh? The reason that we're learning how these things go together is we're going to start using this information in a little bit to predict the actual three-dimensional shape of the molecules. So this water molecule and this ratio that we see in the actual molecule, the molecular formula, 2-to-1 ratio can be explained as covalent and ionic. Hydrogen's being +1, oxygen's being -2. But we can do that either way. We can go through our steps. Oxygen in the center. Step 2, other atoms on the outside. Step 3, single bond. Step 4, 6 electrons for oxygen. 1 times 2 electrons for hydrogen. Gives us 8 electrons altogether, of which we've used 4. 1, 2, 3, 4. 4 electrons left. 1, 2, 3, 4. Okay. And there's the structure, Lewis dot structure of water. And that shows us 2 hydrogens for every 1 oxygen. That explains that particular structure. And here's another example of what we talked about before. You can also have a triple bond. Let's see, we have, nope, that's just my instructions from before. We have nitrogen. Skip this slide, we already talked about this. And we can try out some of these structures. Let's do this one first, and then we'll look at nitrogen as an example of one that actually has 3 bonds between the 2 atoms. Well, let's look at this one first. Give it a shot, pause it, come up with a structure. Okay. Our answer, when you're all done, this is what methane should look like, CH4. It looks like carbon tetrahydride, but it actually has a special name because it's an organic compound, something that we get to talk about how to name in Chapter 6. Okay. Sometimes we have an interesting situation where when we get a Lewis structure, we could equally have done a double bond on one side. Notice how this gives 8, 8, and 8 electrons. Or we could have drawn double bond on the left side instead of the right side. Well, in reality, what we actually have is a single and a half bond. And what that means is it's actually both of these, and it's switching back and forth so fast that what we have is an average 1.5 length bond. That doesn't mean there's actually 1.5 bonds there. It just means that it switches back and forth fast enough that we have what's referred to as resonance. It kind of is a hybrid between the two. Resonance. And that resonance means that we can draw it a little bit differently and think of it as halfway between the strength of 1 and 2 bonds, a single and a double bond, and halfway between the length of a double bond and a single bond. And the way we draw that is with this nice dashed line. So oxygen, 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 plus whatever extra electrons have to be there. Okay? We usually don't show these electrons. Your book does this, but we're not going to show that. We're going to show these extra electrons here, extra electrons there. It's kind of half of a bond. And in fact, this is what your book uses. I don't like how they do it this way. We're going to show it in a more reasonable fashion. Okay? And the way we'd arrive at this, let's look at it. Oxygen in the center. Okay? Single bond to each. We have a certain number of electrons that we can use. We can use 6 times 3 or 18 electrons. 2 and 4 have already been used. So we have 14 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that's where we find that we can shift into the center and form a double bond here, or we could have shifted from the other direction. Okay? So we show it instead as the hybrid form of that 2 possibilities. And that's what ozone looks like. All right, I promised we'd look at nitrogen. So let's look at nitrogen. Nitrogen is also diatomic. Remember, there's those 7 elements that are diatomic. I showed where they were on the periodic table a couple chapters ago. We use the same method. Step 1, nitrogen, that goes in the middle. Other one on the outside with a single line, that's steps 2 and 3. We count up the electrons available, which is 10 electrons. Now we add them in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so not enough electrons. All right? Oops. We used 2. I forgot. So we only actually had 8. So that means I take the eraser, and where's the eraser there? There we go. Alright, so 2, 4, 6, 8, 10 electrons altogether. Nitrogen on the left doesn't have enough electrons by far, so we know we have to have multiple bonds, so we share. Once we share once, we have this. We still have 1, 2, 3, 4, 5, 6, 7, 8 electrons on the nitrogen on the right, but now we only have 2, 4, 6 on the left. So we actually have to share again. So by the time all of them have 8, we actually have a triple bond between the two atoms. That makes this a very strong bond. It's actually very difficult to break one nitrogen apart from another in an N2 nitrogen molecule. It's one of the things that can do that actually is a lightning bolt. The amount of electrical energy present in a lightning bolt can split nitrogen and combine it with oxygen to form nitrates, which the plants can then use as nitrogen in their not vitamins, but need for nutrients. And that's part of the reason, not all of the reason, but part of the reason why plants are so much greener after a lightning storm. Because they're taking this stuff in and they're processing it, and they are in a very happy growing state. So we have oxygen and ozone. Your book talks a lot about this. One of the things we want to point out is that multiple bonds are absorbed by UV light. Or absorb UV light, not are absorbed by UV light, but ultraviolet light, which we talk about in chapter 9, so we're only going to kind of mention it here by name, gets in and isn't strong enough to break a double bond of oxygen, but it does break one of those 1.5 size bonds. So that ozone actually absorbs the sun's ultraviolet light being the one that causes sunburns. And having that ozone there, with its little 1.5 length bonds, which are weaker than double bonds, cracks open, that protects us from having that ultraviolet light hit us and cause damage in our skin. Instead, it just causes damage by depleting ozone. And so that's part of why they talk about having an ozone layer as a protective thing against getting sunburn. Alright, so the shape of molecules. The shapes of molecules come from the Lewis shape, the Lewis dot structures that we've just learned how to make. And this is predicted by something we refer to as VSEPR theory, valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. And this helps us to predict the structures, meaning the actual 3D shape in space of molecules based on their Lewis structure. And so to do this, let's look at some substances. This is really kind of straightforward, but you have to be able to picture three-dimensional shapes. The idea here, and the critical part, is that electrons are going to repel each other. The lone pair electrons that are not involved in bonds, so for instance in our ammonia molecule, which we're showing here, this is our Lewis dot structure of ammonia. We have electrons in these three spaces between the nitrogen and the hydrogen. Those are bonding electrons. And we have these ones by themselves, which we refer to as lone pair electrons. All four of these sets of electrons push against each other. So the result is these electrons will try to get as far away from each other as possible, and to do that they'll form some sort of three-dimensional shape to keep everything as far away from each other as possible. And so the idea is we're going to minimize that repulsive energy, that push on one electron set against another, and that is what's going to give us the molecular geometry. Okay? So 3 dimensions. They jump right into the book, into this 3-dimensional object with 4 things, but we're going to go a little bit slower than that. Okay? we're going to look at something simple. Let's put two objects together. Hydrogen as a molecule, for instance. Its Lewis structure looks like this. So we have a center atom connected to one other atom and no lone electrons. Okay, if you made this a three-dimensional object, what would that have to look like? Well, there's only one way things can look if there's only one thing connected to another thing. That's a straight line. So we refer to this in its shape as linear. Now the next possibility is if you have two things attached to each other. Let's look at carbon dioxide, for instance. If we work out the shape of carbon dioxide as its Lewis structure, we see this. Carbon, two double bonds, one on each side attached to oxygen, and this is the shape. Okay, so for this, we have a center attached to two atoms and no lone pairs. Okay, well, that means there's only two sets of clouds of electrons trying to get as far away from each other as possible. And if you have two things trying to get as far away from a center as possible, what you have is a 180-degree angle, which is still a straight line. So this situation is also still referred to as linear. Okay? Let's look at one additional possibility. How about that CH2O that we looked at before? Okay? That was carbon to an oxygen, double bonded, also attached to hydrogens. And now we have a center attached to three atoms, an oxygen and two hydrogens in this case, and no lone pairs. Okay. So three atoms and no lone pairs. This shape, three things trying to get as far away from each other as possible. We're just drawing the connection directions here. Will form 120-degree angles. So it basically forms like a triangle here. And it's a flat triangle. It's sitting in the plane of the board here that we're drawing. So we call it a trigonal planar shape. Planar, I don't know. Trigonal plane. Okay. So trigonal planar shape. Excellent. That's what things with three atoms connected to the center with no lone pairs form. Okay. And now we've finally worked our way to the first example the book wants to use for shape, CH4. Okay. CH4, methane, its Lewis structure looks like this. Okay. So you can kind of look at this and say, well, I don't know. It kind of looks like these are 90-degree angles. Well, the reality is, though, is we're not stuck in the flat plane of the board. In this three-sided object, the trigonal planar object above, if we push this oxygen further into the plane of the board or pull it directly out of the screen towards us, it's actually only going to get closer to the hydrogens. But here, if we take two of these hydrogens and push them in to the screen, and two more hydrogens and pull them towards us, what we're actually going to come up with is what's referred to as a tetrahedral shape. Okay, so a tetrahedral shape, carbon attached to a hydrogen, and then you can kind of think of this kind of going back into the plane of the board, this one coming kind of out towards us, this one kind of going back a little bit. Okay, so it has this kind of three-pronged stand on the bottom, all connected to like the top point, kind of like a little three-pointed pyramid, some vertices here, the corners, and this tetrahedral shape is actually the farthest that these electrons and the bonds can get from each other. Once we start drawing these three-dimensional shapes, we have to arrive at some way to indicate what that three-dimensional shape looks like. One way is to draw out this whole like little triangle type thing and try to do our best to actually draw this in 3 dimensions with some perspective and do it that way. The other way is to draw these as a line indicating in the plane of the paper or the board that you're drawing it on, a wedge that goes from larger to smaller as being going into the board, and a wedge that goes from smaller to larger coming this way means that this hydrogen is coming out of the plane of the board. Okay, so this is kind of showing that same three-dimensional structure, indicating that this is not just a flat square at 90 degrees. That's not what this forms. This is closer to over about 106, 107 degrees, depending on exactly how all of these things are situated, about 107.9 degrees or thereabouts. Huh? All right, well, that's the simplest four. We can also have other situations come up. Well, one situation would be ammonia. The structure here is a Lewis structure showing attachments to hydrogen, but one lone pair at the top. So here we have a center then, 3 atoms connecting, one lone pair. Well, in one way, with just the electrons, the geometry that we get, we refer to as the electron geometry. The electron geometry is still just tetrahedral because we have 4 things, 1, 2, 3, 4 negative objects, sets of electrons, trying to get as far away from each other as possible. And well, if we have these getting as far away from each other as possible, then what that means is they're going to form that tetrahedron. By 3D perspective here, I am no 3D artist, I apologize. Okay. So it's a tetrahedron, but what bumps into other atoms is going to be these giant nuclei, right? The nucleus of the hydrogen and the nitrogen is much bigger and much more massive in terms of its matter content than electrons are. So when we name the actual shape of the molecule, or the molecular shape, what we're referring to is specifically the nuclei only. So the shape that these form are influenced by the lone pair of electrons, but the name that we give it is going to be based on only the nucleus of each of these. So this kind of 3-pronged pyramid, so we call it a trigonal pyramid shape. Okay, so this is different than a tetrahedron. This is a nuclei as opposed to another atom up at the top here. It's the nitrogen that's in the center that's at the top. And this will have different properties than the tetrahedron that we saw previously. Okay, so anytime we have a center with 3 atoms and 1 lone pair in our Lewis structure, we're going to end up with a trigonal pyramid for our molecular geometry, or our molecular shape. Where this is really made obvious now is in a water molecule. Okay, so our water molecule looks like this. And your first thought might be, linear, right? But it's not. We have a center attached to two atoms, and this works the same way for this as for any that has two atoms and two lone pairs. Okay, so it's not like carbon dioxide where it only had two atoms and no lone pairs. This is two atoms with two lone pairs. So because of this, what we have is a tetrahedral electron geometry. So oxygen, hydrogen, hydrogen, electrons, electrons. Okay, so it's a tetrahedron. You can kind of picture that in 3 dimensions, that kind of pyramid-shaped thing. And now the oxygens attached to the hydrogens, but this is not a 90-degree angle. This is that tetrahedron angle. And in fact, because these electrons aren't really balanced off by anything sharing another nuclei on the other side, they actually push a little harder on these bonds and squish them in. So it's actually a smaller bond than we see in the normal tetrahedral, a smaller angle here. And this is not linear because it's tetrahedral originally. So when we look at just the molecular geometry, the molecular structure, without looking at the lone pairs of electrons, we refer to this as a bent shape. Okay? So this should get us through all of the molecules that we're going to really look at here. Trigonal planar, trigonal pyramid, bent, linear, tetrahedral, etc. Good enough for what we're going to deal with. Okay. So here's just a little bit more of a description of that. Some better pictures than I could draw in terms of the 3-dimensional shape. Another representation that they call space filling. Model of what the atoms look like bonded as a molecule. But we're pointing out there's a difference between the electron geometry and the molecular geometry, but not in this particular example. They're both the same if there's no lone pairs. Then the water molecule, showing a little bit better picture, showing why it's bent. Voila. The electron geometry has 1, 2, 3, 4 things as far apart as possible, so tetrahedral. Water's molecular geometry is just looked at without looking at the electrons, but using the same angles, so that's bent for the molecular geometry. And here's a nice little summary of all the different possible shapes. We didn't do this one. Ozone falls into that. Ozone would fall into that category. Sulfur dioxide falls into this category. But 3 total groups as far apart from each other as possible. 2 of them to atoms. 1 of them to a lone pair. It's going to form a trigonal planar object initially, but those lone pairs at the top aren't going to be considered when it comes time to name the actual molecular shape. So just like water, it's kind of this bent angled molecule. Okay, so boron is another one of those goofy exceptions, so we pointed out here. The other ones in 3A may have 6 electrons and be stable, or 8 electrons and be stable. In reality, for the most part, only boron and sometimes aluminum are ones that have 6 electrons and are stable. So we draw out boron, we draw out its 3 electrons, we draw fluorine. Actually, right, we don't draw the electrons, that's how we draw ionic. We draw boron in the center because it's farthest from fluorine. Fluorine's around the outside, connected by a single bond each. We count up the electrons, 3 for boron, 21 total for fluorine. It's 3 times the 7 that it has. each fluorine has, 24 altogether. 2, 4, 6 electrons used. Gives us 18 electrons to add. 1, 2, 3, 4, 5, 6. That is 8, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. In this case, boron having 6 electrons is stable. The others have 8, so this is the final structure. Boron has 3 bonds, no lone pairs, so 3 atoms attached, no lone pairs. What shape is that? Right, trigonal planar. Whether we're referring to electron geometry or molecular geometry. Alright, so bond polarity. What we have is we have elements that are connected to each other. Those elements are connected by these shared electron bonds. And when they have a shared bond, the protons in one element or the other is going to pull harder or less hard on the electrons that are sharing. So when we have that sharing being pulled harder in one direction, then those electrons are not going to actually be right in the middle of the 2 nuclei. They're going to actually be closer to one atom than the other. So if they were equally distant apart, we'd have the electrons in this bond. Maybe it looks something like this. Right. There's that kind of north, south, east, and west thing, or we can maybe draw it a little bit more like we were drawing the Lewis structures. Okay, and these are the shared electrons. But oxygen is actually as a property called electronegativity that all atoms have. That's the strength of their desire to pull electrons towards themselves. And that has to do with how many protons there are in the center, combined with how many electrons there are between the nucleus and the outermost edge. We're not going to get too much deeper into that idea, but that's just the general idea is number of protons and number of electrons in the way in inner orbits. So a combination between these two gives rise to this idea of electronegativity, which is a measure of how strongly electrons are pulled towards the center. Okay? And if we look at a periodic table, with fluorine over here, and the noble gases not really counting because they don't form bonds, the least electronegativity is in the elements in the bottom left-hand corner. They don't pull on electrons almost at all. Same with hydrogen. It pulls on them somewhat in the middle, but not too much. Over here, in the fluorine, we have the highest electronegativity. Fluorine pulls extremely strongly on electrons, and if it shares electrons with another element, the electrons will be almost on top of the fluorine and nowhere near the other element. So if we look at oxygen and hydrogen, oxygen being right about here, hydrogen being all the way over there, the oxygen has the greater electronegativity. So if we draw these electrons for the oxygen, they're not really shared halfway in between. They're actually closer to the oxygen. So because of that, the oxygen has this partial negative charge near it because it's pulling the electrons close to itself, and that's making it more negative. While these hydrogens are slightly positive, not a full +1 charge or -1 charge, but kind of a partial charge. And this partial negative and partial positive sets up a dipole, two poles, a positive and a negative one, and makes the molecule overall something we can describe as polar, just like we saw in our last lab, right? Or at least the chromatography lab. Okay. So this polar idea can also be drawn with arrows and lines. We point the direction the electrons are going, and we make a little plus on the side that they've left. So we can say in the individual bonds, the electrons are moving in this direction, or we could give the polarity of the overall molecule by drawing that arrow through it and saying that this side then is slightly negative and the other side being slightly overall positive. And just a variety of ways to kind of show the polarity and which side of the molecule has a positive or negative polarity for different molecules. Now the key to this is unequal sharing of electrons. Okay, so all that means is that the two atoms are different elements. As long as they're different, almost always they're going to have a polarity to that particular bond. And then we're going to say whether it has a net polarity by whether or not the polarity of the individual bonds cancel out. So let's see what I mean by that last statement here. Okay, so this is what we just talked about. This is what we talked about with electronegativity, how it increases towards fluorine. Hydrogen's kind of a little bit in the middle because it doesn't have a very big orbital. So something like carbon monoxide, for instance, unequal sharing. Oxygen's the more electronegative of the two. So the polarity makes the carbon side slightly positive and the oxygen side slightly negative. Now, for carbon dioxide, we actually have two poles to this, with a positivity in the center and slight negativity on the outside edges. But because the pole happens in opposite directions, they actually oppose each other and they cancel each other out. Because you're pulling one way and you're pulling the other way equally as strongly. So the overall condition we have is that there isn't a net dipole. We don't have a negative and a positive portion because they cancel each other out by pulling equally in opposite directions. And so that's what this is telling us with this VSEPR theory, whether we have something that is polar because we have differences in electronegativity that don't cancel, or whether something is nonpolar because they have a pole in directions that cancel each other out. Okay. So one more example of this. Screen, there we go. Methane. Three-dimensional shape of methane, and you can only look at the polarity with the three-dimensional shape. It's tetrahedral. Okay, so it has this nice triangular sort of shape. The polarity for this actually gives us a nice dipole along each bond, but they all cancel each other out. It doesn't look like it necessarily. It almost kind of looks like it shouldn't cancel each other out because of how these are arranged. But if we make up this molecule and we look at it in three dimensions, what we're going to see is a set of bonds that all point net towards each other. So the three here are directly opposed by the one on the top. The three here are directly opposed by the one on the other side, and all the way around this particular shape. So even though we have four polar bonds, the molecule is net nonpolar, because all of these in the tetrahedral cancel each other out. Now if we have different molecules, or different atoms in a molecule, I should say, we can look at this and we can set it up our three-dimensional shape. And now we have a pole in all four directions, but since these are different atoms, we're going to actually get a different amount of pole depending on which direction we're going. So we're going to end up with, in this molecule, a slightly negative and a slightly positive side, because even though we have four symmetric directions, the atoms are different in the different directions. So the chlorine pulls harder than the hydrogen in this case, meaning the overall electron direction is towards the chlorines and away from the hydrogens. So dichloromethane is polar, while something with symmetric same atoms on all sides, tetrahedron like this, methane, is nonpolar. So why do we care? Okay? Well, the reason we care is things like the chemical and physical properties of a molecule are determined by things like polarity. The attraction of one molecule to another, all these little positive and negative sides in water molecules attract to each other and help set up a network of attractions that hold the water molecules together more strongly than some other molecule that might be very similar, in a similar shape, like dihydrogen sulfide, for instance, H2S, which is polar, but not quite as polar. Okay. Less polar. This is a gas at room temperature because the molecules don't hold to each other as easily. And we can have water, which is a very similar shape, but a stronger dipole, the oxygen versus sulfur. More polar. Okay, so this is a liquid at room temperature and forms a solid relatively easily. You just have to get to 0 degrees Celsius, right, or 32 degrees Fahrenheit. And something like carbon dioxide, which is a larger molecule, right, because it has two oxygens and a carbon instead of two hydrogens and an oxygen. So this is heavier, has more matter to it, more material, yet because it has a non-polar structure, even though it's heavier, this will still be a gas at room temperature, because it being non-polar means that one of them is not attracted to another as strongly as the polar molecules are attracted to other polar molecules. So what this gives us is this gives us a set of properties, such as how easily you can boil things, how easily you can freeze things, whether or not things mix with each other or not. It gives us all sorts of properties that we're going to learn about in a great amount of detail around chapter 12 after we've learned a lot more about shapes and that sort of thing. But I just wanted to kind of introduce you to that idea now as to why in the world we care whether something is tetrahedral or linear, polar or nonpolar. We care because it explains to us and helps us predict all of the chemical and physical properties of that material. Okay? So, answer this question: is this particular structure polar or nonpolar? Right? So it's a tetrahedron because we have four directions in space. Tetrahedral. Okay? These bonds are polar because carbon and fluorine are not the same thing. The electrons are moving out towards the fluorines. But in a tetrahedron, those are symmetric directional bonds, so the net polarity is all canceled out, meaning overall, this is non-polar. So the carbon to fluorine bond is polar, but overall, the molecule is non-polar because those polarities cancel each other out. How about BF3? Boron trifluoride. Well, we set it up here. Boron, fluorine, fluorine, fluorine. We figure out our available electrons and how many we've used for the Lewis dot structure. We come up with this. Boron doesn't need a double bond because it is that special case that only needs 6 electrons to be stable. So this is the final structure. Lewis structure. 3 atoms, no lone pairs, trigonal planar. Trigonal planar. This pole is canceled out by these 2 poles. This one is canceled out by those 2. So this molecule, with being in a trigonal planar shape, is symmetric so that the different poles cancel each other out, making this one also nonpolar. So we've talked about all these things: ionic bonds, covalent bonds, Lewis theory, which is where we talked about how we can form these different bonds based on electrons becoming an octet arrangement for the atoms, and then how that led to the Lewis dot structure we talked about how to make. Then we talked about how they have to point in different directions in space so that the electron pairs can keep away from each other, and how that leads to polarity. Now, let's think about this for a second, because we're getting to a pretty exciting point here. We're not quite there, but we're really close with this chapter. We are at the point now where I can tell you the name of a molecule. From its name, you can give me the chemical formula. From the chemical formula, you can give me the Lewis dot structure. From the Lewis dot structure, you can give me the molecular geometry. From the molecular geometry, you can tell me if it's polar or not. From polar or not, and this is the part that we're going to get to here, you can tell me about its relative chemical properties. So we're one step away from me being able to just tell you the name of a molecule and you being able to tell me what that chemical will be like just from its name and working out the other steps. I mean, that's the basis of chemistry, is understanding chemistry and knowing about the chemistry, how it's going to react, and how the material's properties are going to be purely from the name. So this is an exciting point, and we're almost there. Almost there.